That old timer snuck up on me again, and I was talking just as and everything just all of a sudden cut off. Anyway, the extent to which an acid donates a proton depends upon the strength of its conjugate base, as I was mentioning. If this is a strong, whatever this particular ion is right here, is a strong base, then any proton donated to a water molecule is recaptured by that particular ion. So little hydronium ion would exist in solution, and therefore this would be a weak acid, right? So the stronger this is as a base, the less you're going to get of this. So if this is a weak base, it's unlikely for this to be recapture a proton, and therefore a large amount of this would exist in solution, and therefore this would be a strong acid. Here are some relative strengths of those, okay, of the different ones, and the relative conjugate bases, okay. And this is HClO2, and you see that it works just the opposite way. Acid strength is inverse to base strength, okay. So this is a stronger base, this is the weaker base. This is the stronger acid, these are the weaker acids. Conjugates of weak acids and weak bases are weak bases and weak acids respectively. These conjugates compete with water. Solutions of weak acids and bases produce an equilibrium mixture of reactants and products. Just keep in mind that for conjugate acid-base pairs, the following equation must always be satisfied, right? That's what I was trying to point out before. That this constant times this constant equals Kw, and it's always going to be equal 1 times 10 to the minus 14th. There are several ways to determine these. One is to measure the pH of a solution prepared by dissolving a known amount of that in these, and that gives you your pH, right? Given some information that we can use to find the initial concentration, or you can just calculate these. So these are different ways from information to calculate what these values are going to be. I'm not really going to require you to do that on a test. You should have a general idea about the relationships of these in terms of percent ionization, but I mean that's about as far as I'm going to take it with you, okay? I want you to be able to calculate a pH value and a pOH value, and I want you to be able to calculate percent ionization, but that's about it, okay? So, the percent ionization of a weak acid. Here you have the concentration of this divided by the concentration of this, right? So that you calculate the percent, because this right here equals 10 to the minus 2.09. And if you take the log of this right here, it's going to be 0.0081 moles. So you have this molar concentration times how much you had in there, okay? That means you have 6.5% ionization, okay? So the process is similar to that used to calculate equilibrium concentrations. So that given any Ka or Kb, and given some information that can be used to find the initial concentration, you can then calculate these concentrations of these ions, and from these you then calculate what that pH value is. When we do a lab on pH and pOH, I'll go through the calculations there in great detail. A neutral solution contains equal concentrations of hydronium and hydroxide ions. The reaction between an acid and base is called an acid-base neutralization reaction. That's exactly what we talked about last week when we were talking about all the different types of reactions, right? So the resulting solution is not necessarily neutral when even when the stoichiometric equivalent quantities of acid and bases are used. That's because the salt formed determines whether the solution is acidic, basic, or neutral. For example, if you have a strong acid and strong base, you do get a neutral solution and a salt is formed. So water and salt is formed. But if you have a strong acid and a weak base, this is going to, a weak acid solution forms, right? And if you have a weak acid and a strong base, a weakly basic solution forms. And this, a weak acid, weak base, it depends upon what their constituents are. It could be either one or the other, okay? So this tells you what you can expect from these different ones. For example, sodium hydroxide plus hydrochloric acid forms a salt and water. This is completely dissociated, so this is going to be almost completely a neutral solution, okay? So if you have the same molar amounts of each of these, you're going to end up with a salt and water, and that's all you're going to have. If instead you have hydrochloric acid with a weak base, then you're going to have this material and this. The salt is going to be of this form right here, okay? So this is just should be NH4OH here, not Cl. This is not correct. This should be NH4OH going to NH4Cl plus H2O, right? But this right here is a salt formed, and it is going to be a weak salt. Here you have a weak acid and a strong base. They did get this one correct. And here, this right here is a salt that is formed. And the degree to which this dissociates means that you are going to have, this is going to be more basic, right? Just like the prior one was going to be slightly acidic. Here you've got a weak acid and a weak base. Then, this is the salt that is formed, and it depends upon the exact concentration as to whether this is going to be acidic or basic in solution. So, when we were doing these, we had these concentrations initially, and 0 of these, right? So here, and this is benzylamine, right? And then this is going to decrease in concentration. These are going to increase in concentration. So at equilibrium, whatever this decreases by, each one of these will be increased. So these are the different salts and many of the different ones that you can have for these, okay? Alum, this is medicine, canning, baking soda, and the different ones that are formed. And each one of them undergoes a different type of equation reacting with an acid and an action of an acid and a base reacting to form water and a particular salt. Now there's another thing called a buffer. A buffer is a solution containing appreciable amounts of both weak acid and its conjugate base. Okay, so it's a weak acid and a conjugate base. Sometimes it's a weak base and a conjugate acid, but that's fairly rare. Usually it's a weak acid and a conjugate base. Buffer solution resists changes in the pH by the addition of a small amount of acid or base. For example, acetic acid, acetate ion, or the bicarbonate. Well, the reason why your blood is neutralized or has a wide range of pH is because of the bicarbonate ion in there causes it to have a range that you can either add acid or base to it, and it's not going to shift that pH very much. Acetate ion also is very frequently used as a buffering material. For example, here you've got an unbuffered material right here, and this right here is buffered with that sodium acetate. If you add something 1 milliliter, just 1 milliliter, that's about 3 drops, a 0.1 molar HCl to this unbuffered, you can see it really changes from this color to this color. But you're adding the same amount to this one, and it shows very little change at all, right? This is the methyl, it turns red at a pH of about 4. So this has gone from a low value, really up quite high, okay, with just the addition of 1 single milliliter. That's the advantage of a buffered solution. So buffers are good at getting rid of strong acids and bases. You're adding, they're consumed, and so they don't directly affect that pH. So if you want to have a stable solution throughout a given range, you can buffer that solution so that any added hydroxide ion is just going to be converted to a weak base, right? Any added hydronium ion is going to be converted to a weak acid. So what these do is they maintain a nearly constant pH. You can see another example here where you had this ion, and adding hydroxide ion is going to shift this in this manner, right? And so this changes slightly here and a little bit here. This changes slightly here and a little bit here. So you can see that over a range of adding either a base either adding a base in this direction or a buffer or a hydronium ion in this direction has just a slight effect on the overall pH of the solution. The buffer capacity is the amount of strong acid or base that can be given, added to a given volume of buffer before the pH changes. It's how much can that buffer soak up of the hydronium ion or the hydroxide ion before the pH starts to really change. We're next going to talk about acid-base titrations, and we can analyze acid by reacting with a known concentration of the other, right? Strong acid, strong base, weak acid, strong base. These are the two that you're going to have in the lab next week. The equivalence point is the amount of titrant added is equal to the amount of the analyte present. The analyte is what's in the beaker down below. The titrant is how much you've added from the burette up above. If it's a strong acid, strong base, pH is 7 at the equivalence point. Okay, and so here it's initially very low. There's a very gradual rise as you add more of this base to there. Eventually the pH will rise rapidly, and at the midpoint is vertical. It's the equivalence point, and then beyond that point it changes and rises again. Okay. Instead, if you look at a weak acid and a strong base, many of the things it starts off low, but not quite as low. But it's going to start, as soon as you start adding some of the base, it's going to start having a change, and it's going to start increasing and then have a gradual shift as it goes through the titration equilibrium point and then leveling off again. Okay? And this just goes through the equivalence point here is 8.72 as opposed to just at 7.0. This gives you an example. This is acid, strong acid being titrated with this base right here. So as you're adding more milliliters of this NaOH, you can see how it's very slow to change, and then a very steep change right here, going all the way from about a 3 all the way up to about an 11, and then rounding off again. As opposed to that, with acetic acid and sodium hydroxide, you can it starts off and immediately it starts shifting upwards, doesn't it? And then you have a fairly narrow range here, so that it's almost at this point right here before it starts to its dramatic increase. And you'll see that this right here is pH of 8.72. Quite a bit, not the same as there, right? That's because of that KB and Ka type of calculations. 1 or 2 drops of indicator are used. Acid-base indicator is useful to determine the equivalence point. And here, this gives you an example of different ones that can possibly be used and the range over which they're really useful. Okay, some of the key ones are phenolphthalein and that, and litmus paper is useful right in this range. Phenolphthalein is up here, methyl orange is down here. And that's about all I can do in that one. There's just a little bit more that we're going to have for the next one.